Good morning, everyone. Today we're going to start talking about vector calculus. We're going to continue talking about integration, and we're going to start with the first kind of integral, which is the line integral. So thinking about integration, you really can. Let me see if I can fix this. Okay. So thinking about integration, you really can integrate in any number of ways. So let's say that this is 3D space. All you have to do to integrate on a line is to select your line first, right? You have to select your curve. So you say this is the curve, and then you move along the curve and you integrate, you sum a function. And this function could be anything. This field that you're summing on, your summing could be anything. It could be a scalar field. We could integrate a scalar field. We could integrate, of course, a vector field. However, when we talk about line integral in physics and EM theory, it's much more common when we move across a line. It's much more common in physics and EM theory. It's much more common to talk about the sort of line integral where we are summing up a vector field, and not just any vector field randomly. So when we talk about line integral in general, we are talking about a really specific kind of line integral. What are the possibilities? Well, I could move along a line and I could sum up a scalar field. So at each, let's say I have a temperature field. So I have some temperature, and then I move along the line and I sum up the temperature at every point. So I'm integrating a scalar field. This is one way of doing it. Another way of, so here the input, so to speak, to the integral is a scalar, and then the output is a scalar, right? I could do another sort of summation. Let's say I have a wind field, like wind speeds everywhere in space. I could move along the path, and then I could sum up the vector at every point. So I'm adding up vectors together. So in the end, my sum would be a vector sum. So the input into the integral, what I'm summing up are vectors, and then I sum them up and I end up with a vector, right? So those two kinds of line integral are possible, but they are not the line integral we are talking about. So those two kinds of line integrals are not the line integral we are talking about. The line integral that we are talking about here that has the relevance to physics and EM is what's called the work integral, the sort of integral that if you have a force field, gives you work. So this sort of integral, line integral, is like this. So if I have my path, and then I have, let's say, a vector field, I have at every point in space a vector. So let's say here I have a vector. So every point in space has a vector associated with it. Doesn't matter what point you select a point in space, it has a vector associated with it. So the kind of relevant line integral here is the line integral where we move along the path, and at each point in the path, we don't, let's say the force vector or the vector at this point is this vector, right? At each point in the path, we take a differential element dl, the differential segment or differential displacement dl. At each point in the path, we don't sum an actual vector, we sum the projection of this vector on the path. So what we're summing actually, so let's call this f. We're summing f dot dl. So at each point along the path, we're taking the projection of the vector. We're taking the component of f that is on the path. So this is f on path. So we're taking the component of the vector that's on the path and we're summing that up. This could make sense in let's say you have something like a boat on the ocean, and you want to find the component of the wind speed, let's say, that does work on the boat along its path, right? So this is where would this arise, right? So the kind of line integral that makes physical sense, I'll write it down now, is the kind where you have a vector field f, which is a vector field across space at every point in space, and then you dot it. This is a dot product with a segment. You dot product it with a segment, line segment, dl, displacement segment, and then you have a multiple of segments like that, form a path, and you're summing up this dot product. So from point P1 to point P2. So this is the sort of line integral that we really care about in physics and EM theory. This has physical sense. The other sort of line integrals, I mean, could have their applications, but they don't make physical sense. The one that makes physical sense is we select a path, and then whatever force field or vector field that exists, we take its component along the path at every point, and then we sum that up, right? If F is a force field, meaning it's a field that represents a force at every point in space, force in the physical sense, the thing that you measure in newtons, the thing that can move masses, then this integral is really familiar to you. You really know it already. This is called the work integral, right? And it makes sense. Force times displacement gives me work, right? Whenever you have force, right? So whenever you have force and then you have a displacement in a certain direction, dl, infinitesimal displacement, the way to calculate the force is to find the component of the force in that direction, right? F dot dl. So this is the component of the force in the direction of the displacement. That is the work. And then the total work along a curve is the summing up of the work for each segment, right? The force in the direction of the displacement, their product is work, right? So, so this is called work. And dl, of course, we learned already how to express it in different coordinate systems. Where space is not just, we want to describe the space precisely in a coordinate system, right? So we learned that in Cartesian coordinate system, we can decompose this as x, dx x hat, plus dy y hat, plus dz z hat. Right? So this is an example. So work is an example. Right? But in general, the result of the integration is some scalar, q. We're integrating over a curve. C stands for curve, and it's some vector field. It's some vector at it's a vector at every point in space. We move along segments, infinitesimal segments on that curve, dot dl, right? So this is A, and then we're moving along a path, curve, right? And an infinitesimal segment here, an infinitesimal displacement is dl. And we're moving along each segment on this curve from the starting point to the end point. And we're doing this. I can write this, I can apply the geometrical interpretation of the dot product, right? I remember we studied that. This is just going to be the integral of A, magnitude, dl, magnitude, cosine theta A dl, the angle between A and dl at every point. So this is one way of doing the integral. Or we can recognize that A can be decomposed into components with respect to the Cartesian basis, and dl, we already know how to decompose it into components with respect to the Cartesian basis, and then we can take the dot product. So I decompose A into its vector components, and I compose dl into its vector components, and I take the dot product. So I end up with three dot products, right? It's sum of three terms, and integration is always going to be linear over summation. So I can write Q as equal three integrals: an integral of A dot x hat dx plus A dot y hat dy plus A dot z hat dz. So this is another practical and much easier way of doing this integration. Let me introduce a definition. So there's something called a closed path integral. The closed path integral is simply an integral where the path of integration, let me go back to my space here, is just a path that goes back. It's like a snake that eats itself. It starts at a point and it goes back to that same point. It's a closed interval. It's a closed path. So a closed path interval, the way you write it down, and many textbooks and authors use it this way, I like it, is I like this method of writing it down, is to write it as follows, is to write it as an integral with a circle in the middle. The circle in the middle, and C to signify a curve. The circle in the middle means it's a small curve, it's a closed curve. So A dot dl, right? And this is just over the same thing. Right? This has another name. The other name this has is circulation. So we call this also circulation of A around curve C. Right, so this would be some vector field A, and then I have my curve is a closed curve. So this would be, when I do this calculation, this is called the circulation of A across curve C. And this has a lot of applications in physics and in EM. This will arise a lot when we discuss Ampere's law, for example. Right? This circulation has an important physical meaning. Right? So this is not mathematics. This is physics. We're introducing the mathematical language, but there is a lot of physics here. If for a certain vector field that is a force field, let's say, if this, well, not a general vector field, if circulation is 0, this is what we call the conservative field. The line is too thick, isn't it? Right? This is a conservative field. Or another way of calling it, it's a restoring field. Right? So this is a conservative field. Maybe thicker is easier to clearer to see. Restoring field, okay? So if it's 0 along any closed path, okay? If it's non-zero, then we say this field is non-conservative. Right? Gravity, for example, is conservative, because if this is work represents work, for example, for a gravity field, A is a gravity force field, then starting from a certain point and going back to the same point brings you back to the same potential energy. So the work done to go back to the same point is 0. Okay. So let's do an example. Let's do an example where we show how to do this integral calculation. So example, and I'm gonna do example 2.1 from the textbook. Okay, so a vector field is given. So a vector field is given as follows: f 2x x hat 2y y hat. Right? So this is how we describe the vector key field in the Cartesian basis. So this assumes a space where we have a Cartesian coordinate system and we have a basis at every point, that is the Cartesian basis, x hat and y hat. We know how to derive the basis. At every point you see where the coordinate is increasing, and that gives you the unity vector in each direction of coordinate increase is the basis. And at every point in space you have a function that gives you f, what f is, both the direction and magnitude. Okay. So if f is a force field, let's find the work done by moving. Let me sketch the force field here. So what happens if x and y are 0? The force field is 0. What happens if x and y both increase? We get a bigger field. The sketch could look something like this. So at every point, as x and y increase, the field increases, right? So I'm not going to draw the whole thing, but you get it. It's a radial field. It's a radial field. So as we go away from the origin, the field increases. Okay. Right. So F is a force field. What is the work done? Let's say we move some particle moves on the XY plane. So forget about the whole 3D space for a while, for a second, and let's assume that there's movement only on the XY plane. Okay. And anyway, the force, by the way, this should be like the XY plane. Notice something particular. This is XY. Notice something peculiar about this field. It has no Z component, meaning that it only has components. The vectors lie only on the XY plane. So if you move in the Z axis, you get the same thing. It repeats at every plane, at every point Z. So if you move to any Z, any height, you will get the same picture. You get this radially outgoing field from the origin. Okay. So anyway, on the XY plane, let's say we move from point P2 50. We're ignoring the Z axis because there is no Z component here. And then, or let's assume this is a two-dimensional space, right? It's fine. And then we go to point P3 03. Okay, so we want, this is our path, this is our curve. Okay, so we want to integrate, we want to find the work going from P2 to P3. So the work is the line integral P2 to P3 F dl, and then we know how to describe each of those terms here in terms of the Cartesian basis. So this is from P2 to P3. This is already given to us, 2x x hat plus 2y y hat dot, and we know how to do the differential element in Cartesian coordinates. It's going to be dx x hat plus dy y hat. And we know how to do this dot product. We just do the distributive property. So this is going to be from P2 to P3. Just multiply this with this, and then add plus this with this. That's all the dot product is for an orthonormal basis. We already established that in a previous lecture. So this is going to be 2x dx plus 2y dy. And then we can separate the integral 2x dx, right? The integration always can be distributed over a sum, 2y dy. Now here the key thing is we want to determine the limits, right? So as we're moving across the path from start to end, how is x varying? We start at 5, right? And we end at 0. So x goes from 5 to 0. How is y varying? Y is varying from 0 to 3. Right? And that's all there is to it. And now we can integrate each one of those separately, right? So this is going to be 2x is x squared, 0, 5. You know how to do integration. 2y is y squared, 0, 3. So this is going to be 0 squared minus 5 squared. It's going to be minus 25 plus 3 squared plus 0 squared plus 3. So this is going to be minus 16 joules. Okay, so this is the work done going through this path here. All right. There's a part B to this example. Let's say we integrate. We start at the P2 and we end at P3, but we take a different path. Let's say we take a different path. Okay. So let's say our path is as follows. So this is P2. I'm starting at the same point, 5, 0. And I'm ending at the same point, P3, 0, 3. But now my path is as follows. I'm hitting the origin first, and then I'm coming here. This is my path now. So I'm hitting P1, 0, 0. What would the integral be in this case? Well, it's we have two linear segments, right? Because we have two segments, we can divide the integral into two parts. I can, this is a basic property of any integral. You can subdivide it over subintervals. So the whole integral can be written as the integral from P2 to P1 f dot dl plus the integral from P1 to P3 f dot dl. What would happen if this was a conservative force, by the way? If this was a conservative force, so this is the first path, and then this is the second path. If this was a conservative force, what this means is that the integral, let's say on this loop, is going to be 0. So if I start at this point, go here, and then go here, and then come back, the whole integral is going to be 0, which means that the integral from here to here is going to be minus the integral going from here to here, which means the integral, if you integrate in one direction and you reverse the path, right? If I integrate in this direction, but then I reverse the path, the result is going to be negative, right? That makes sense because I'm going in the opposite direction, right? Similar to integration in one dimension. If you go from A to B, instead of going from A to B, if you go integrate from B to A, you will have a negative sign, right? So that means if the force is conservative, you know, this plus this equals 0. That means this integral equals minus this integral, right? Minus this integral is this integral. So that means integrating from this point to this point should equal integrating from this point to this point. Another way of stating the conservative field property is that it doesn't matter what your path is. If you start at the same point, P start, and you end up at the same point, the integral is going to be the same. So this is just a corollary. This is just a lemma. This is like another way of stating the conservative property. We stated it as a closed integral being 0. Another way of stating it is that it doesn't matter what the path is. If I integrate along this path, or this path, or this path, or this squiggly path, the integration is going to be the same. The integral is going to be the same. So if the force is conservative, we might guess, hey, maybe this integral will give us the same result. We will get minus 16 joules. It's not a necessary condition. Like if you integrate along two paths and you get the same result, that does not mean that this force field is for sure conservative. You might have been lucky and you have selected two paths that by luck gave you the same result. Right? But let's do this example along this different path. So this is going to be the integral from P2 to P1 of 2x x hat plus 2y y hat dot dl. Now the cool thing here about this path is that we are not traversing any y coordinate, right? Y is 0 along this path, right? Along this path there is no dy component. Dy is always 0 because y is not changing as we're moving along this path. So the differential element is just going to be dx x hat. There won't be any dy, right? Plus now P1 to P3, 2x x hat plus 2y y hat dot. Now along this path here, notice that x is not changing along this path. Because x is not changing, in the differential element, dy is going to always be 0, dx is always going to be 0, so the differential element is just going to be dy y hat. So if we do this, this is going to be, this can be decomposed into 4 integrals. So this is going to be P2 over P to P1, 2x times dx, so it's going to be 2x dx, right? And then the y component, there is no y hat here, so this is going to go away, right? Plus, sorry, 2 integrals, P1 over to P3. This is going to go with this, the 0. There is no x hat here. So y hat component times y hat component, this is going to be 2y dy. So this is going to be the integral. X is going here from 5 to 0. So it's going to be 5 to 0, 2x dx, plus the integral. Y here is going from 0, changing from 0 to 3. So it's going to be from 0 to 3, 2y dy. And this is exactly the same thing we got here, right? So this is going to exactly give us the same result. So all we can say here, right? So because integrating along this path equals the integral along this path. So the integral across the loop, in a loop, is the integral along this path, and here we're moving against the integral that we calculated, so we multiply it by a minus sign, but this is equal to this, right? So something plus its negative is going to give me 0. So this field, the integration along this closed path is 0, right? But this is not enough to determine that the force field is conservative. This is not enough. It has to be 0 along any path. So the only thing we can say here is that this field might be conservative. To prove that a field is not conservative, it's okay to show one counterexample. It's okay to show one path where the integral is not 0 along a closed path. If we can show that, then this is for sure not a conservative field. So you only have to do one example. To prove that a field is conservative, you need to show that somehow, you need to find some way to show that this field this integral along a closed path is 0 for all possible closed paths. Okay, so it's a bit trickier to prove that a field is conservative. Right, now we're going to consider another example. There's something interesting we can say about this problem. Notice that when we separated the integral, it divided nicely in such a way that when we're integrating with respect to dx, whatever function we're integrating here was only a function of x. It wasn't a function of y. If we had some y here, so this integral would have been more complicated, because as x changes along the path, y also changes. So y would be a function of x along that path. So this integral would have been more complicated, but it kind of simplifies nicely because it's of course a contrived example where the x and y component of the f field are such that when we separate the integral with respect to dx ends up being just a function of x, and the integral with respect to dy ends up being just a function of y. That's why for this particular example, this path didn't matter much. I mean, I could have had a path that's, like this, and we'll still get the same result because of this nice separation quality, right? So we can say that for this kind of specific field, we can easily show that, yeah, this is a conservative field, right? But it's not going to be the case always. That cannot be easily shown at all times. Okay, so now let's move to a little bit more difficult example where this nice separation does not happen. Okay, so that's the point of the next example, to show you like a more typical scenario where this nice separation does not happen. Okay, so next example is about calculating the circulation of a vector field. So let's say I have a vector field A, xy x hat plus y hat 3x squared plus y, and I want to calculate the circulation of, again, this is all in 2 dimensions. There is no z dimension at this point. I'm using Cartesian coordinates, and the path I wanna calculate the circulation on is the unit circle. So this is my path. What's the equation of the unit circle? It's x squared plus y squared equals 1. Right? That's how you know that you're on the unit circle. Okay. So the integral, so it's a circulation, so that's why it has a circle here. L A dot dl is just going to be the integral of the x component dx plus the y component dy, right? This is the dot product. So this is going to equal, what's ax? Ax here is xy, right? Xy dx. And then what's ay? Ay is 3x squared plus y. Notice here we don't have the luxury when integrating with respect to dx, we don't have the luxury of this integrand being just x or functions of x. Y is involved there. Okay, so as we move along the circle, y is going to be a function of x. How will y be a function of x as we move along the circle? First, how can we achieve this integration, by the way? So we have two integrations that we have to do. Well, how can we easily do this integration around the circle? What we could do is we can separate the circle into arcs. So I could start at point P1 here and first integrate along this arc. So this is the path L up to point P2. And then I can integrate along this arc. So this is the simplest way of achieving this integral, right? P2 to P3. And then I integrate along this arc, P3 to P4, and then I integrate along this arc. So here I subdivided by each integral here into 4 parts. Right? I need to do it in 4 parts because I'm going to get a unique, along this path, each arc is going to have a unique equation for the path. Right? I need to write how x is a function of y or y is a function of x. Right? So I know that x squared plus y squared equals 1. So along this arc here, x is going to be, so this is xy, by the way. X is negative here. So x is going to be, because x in general is going to be 1 minus y squared square root. But square root could be positive or negative. Right? So it's a selection of positive or negative that gives you different arcs here. So x is going to be, because x is negative here, because positive x is here, positive y is here, so x is going to be minus square root 1 minus y squared. This is how x is a function of y, along this arc here. And then this is for this arc. And then y in this positive, in this case, is going to be 1 minus x squared. Okay. What about this arc? And this arc, x and y are positive, so x is going to be square root 1 minus y squared. This is the circle equation. And y is going to be square root 1 minus x squared. And then along this arc here, well, y is negative, x is negative. So both x and y are going to be the negative selection of the square root. The negative square root minus, right? Because whenever you solve this equation and you take something to the other side and take the square root, you have an option to select either positive or negative. That selection is essentially a selection of one of those arcs, right? So x is going to be minus 1 minus y squared square root, and y is also negative, so it's going to be minus 1 minus x squared square root. For the final arc, x is positive and y is negative, so x is going to be square root 1 minus y squared. Y is going to be minus 1 minus x squared square root. Right? So this allows us to write x and y as functions of the other coordinate for each arc. And this allows us now to carry the integration easily here. Okay. So let me go back to black. So the a dot dl. So here I divided the integral into 4 parts. So I'm first gonna go from P1 to P2, right? And what is the integrand? xy dx plus 3x squared plus y dy, right? So I'm joining them together at this point, right? Plus P2 to P3 going across the second arc. I'm gonna repeat the same thing. I don't want to write it down again. Uh-oh. Zoom out. And then the same thing, integral from P3 to P4, the same integrand. And then I'm gonna integrate from P4 to P1. Right? So so we divided the path into 4 arcs according to the form of the functional dependence between x and y. Okay, so let's calculate the segments separately. So let me calculate the integral from P1 to P2. The integral from P1 to P2 a dot dl, right? So, and let me separate dx and dy. So x is going in the first arc here. X is going from 1 to 0, and y is going from 0 to 1, right? So this is equals the integral from 1 to 0 xy. But how is y a function of x in this segment, in this arc? Y is a function of x using this formula, right? So I'm going to write x square root 1 minus x squared dx. And then I integrate, y goes from 0 to 1. How is y a function of x here in this segment? Y is square root 1 minus x squared, right? How is x, sorry, a function of y? Because now I'm doing the dy integration. X is a function of y using this formula, 1 square root 1 minus y squared. Right, so I need to, instead of x, I need to put square root 1 minus y squared. So square root 1 minus y squared squared is just 1 minus y squared. So I end up with 3 times 1 minus y squared. So I end up with 3 minus 3y squared plus y dy. This now I can integrate easily. Right? This is just becomes an integration problem. You have to kind of go back and review how to do different integration problems, right? So this I guess let me do the first one here. This I can do by substitution, right? X 1 minus x squared dx. How do I do this? Let me do the indefinite integral, right? So I can let u equals 1 minus x squared, right? 1 minus x squared square root. What is du then? Du is going to be minus 2x over 2 1 minus x squared. You know, like how do you integrate d square root x over dx, right? That's just 1 over 2 square root x. That's it. So this is what I did here. This is a square root, so it's going to be 1 over 2 square root 1 minus x squared, and then I use composition, right? I use the composition property. So I integrate the square root, differentiate the square root, and then differentiate what's inside the square root, which is minus 2x. You have to review this stuff, right? dx. But I know square root 1 minus x squared is u, right? So this is going to be minus 2x over 2u dx. 2 cancels with 2. So I end up with dx being minus u dx over x. So I continue the substitution. So I say integral x 1 minus x squared dx is just going to be minus, instead of dx I put this in, so instead of dx I put in sorry, this is du here, instead of dx and put in minus u du over x cancels with this x, right, and then end up with minus integral u squared du. Why u squared du? Because this is u, right? So my u times u gives me u squared du. So this becomes minus u cubed over 3, right? So this is the indefinite integral. So the result, the end point is that x 1 minus x squared dx, the indefinite integral is going to be minus 1 minus x squared 3 over 2, half is the square root, right, over 3. So you need to kind of go back to calculus and review how to do those simple integrals, you know, either through the substitution method or the integration by parts method. So this is like a muscle you have to kind of train a bit, right? The point is not doing the integration. The point is just, you know, remembering how to do it from calculus. Right, so I'm not gonna I'm gonna go through examples and homeworks, and you're gonna practice that. But ultimately, you have to kind of build that muscle back up that you developed when you studied calculus. Okay, so okay, that's the point. I wanted to get this. So going back, the integral from P1 to P2 a dot dl is gonna be what? Is going to be, we know how to integrate this now, right? So I found that, right? This is this. So this is going to be minus 1 minus x squared 3 over 2 over 3. And this is from 1 to 0. And then what about the second part of the integral? Excuse me. The second part of the integral is easy. I don't even need to do substitution for this part. Right, so this is going to be 3y and then y cubed of y cubed and then y cubed y squared over 2, right? So this is going to be plus 3y minus y cubed plus y squared over 2. Second part is easy. And then we do this integral. So if I evaluate this at 0, it's going to be 3 to the power 2, which is 1, minus 1/3, minus evaluated this as at 1. Let me see, at 1, this is 1 minus 1, 0, so it's going to be 0. Okay, then we take the second part, evaluated at 1, so it's going to be plus 3 minus 1 plus half. Minus evaluate this at 0, it's going to be 0. So this would be the result. This would end up being 13 over 6. Okay, so we've knocked down one of 4. And then now here we have to do the second integral. So we have to go from P2 to P3 a dot dl. So what about the second segment? This is the same. 1 minus x squared dx plus 3. Okay, for the second segment, which is this segment here, y is the same as here, so the first integral doesn't change. X, however, here is negative, right? But does it matter here, right? Because it doesn't matter because x is squared, so it doesn't matter whether x has minus sign or positive sign in front of the square root, because anyway in the second term here we square x, so it's going to be the same really. Only the limits of integration are going to be different, because here x now is varying from 0 to minus 1, and here y is varying from 1 to 0. So the integral here, the integral limits are going to be 0 to minus 1 and 1 to 0, and this is going to be the same really, 3 minus 3y squared plus y dy. And we already know how to do this integral, right? This is minus 1 minus x squared 3 over 2 over 3, evaluated from minus 1 to 0 to minus 1, plus 3y minus y cubed plus y squared over 2, evaluated from 0 to 1. Do this integral. I end up with, if you do this, let's see, you end up with 1/3 minus 3 plus 1 minus half, which ends up being minus 13 over 6. Will this result be 0? We don't know yet. Okay, so let's do now the integral from P3 to P4 a dot dl. So here in this third interval, x is going from where to where? X is going so x is going from minus 1 to 0. Y is going from 0 to minus 1, right? However, here when we substitute y has a negative sign in front of it, right? X, we said, doesn't matter for the second part because it's x squared anyway, but there will be a minus sign coming from here, right? So the integral here is going to be integral from minus 1 to 0 minus, there's going to be minus sign here, x square root 1 minus x squared dx. Y here is going from 0 to minus 1. You have to be careful with the limits of integration. 3 minus 3y squared plus y dy. And if you do this integration, we already know how to integrate this. We already know how to integrate this. We don't have to repeat it. We're not going to repeat it, but this is going to end up being minus 7 over 6. I'm going to leave the last segment for you as an exercise. But the last segment, P4 to P1, a dot dl, is going to give me 7 over 6. So the total integral, a dot dl, is going to be 0. 13 over 6 minus 13 over 6, and then 7 over 6 minus 7 over 6. So the result is going to be 0. So this force might be conservative. Remember, we have to prove that the circulation is 0 for all possible paths. All right. So we're going to continue next time with integration and do more problems. So next time I want to redo this problem, but let's say we redo it in a different coordinate system. Notice here our path is circular. It's a circle. So this would suggest that maybe this integration would be simpler in a cylindrical or a spherical coordinate system because of the symmetry, because of the circular path. So we're going to explore this thing, this possibility next. And just to show that we're going to get the same result if we change the coordinate system. And just also to exercise how would we go about changing the coordinate system, doing a change of coordinates. Okay, so I'm going to continue with this next time. See you next time, guys. All right, bye.